Hello chemists, this is Ms. Placino and you're watching lesson 4.6 on polarity. Today we're going to discuss how we can determine if a bond or molecule is polar or nonpolar. Some goals for today's lesson. We'll understand that differences in electronegativity can be used to predict polarity. And we'll use that specifically to predict the polarity of a bond. And a little bit more complicated, but we will be able to predict the polarity of a molecule. These last 2 points are the big ones. All right, let's go ahead and get started. We'll start off with bond polarity, as it's conceptually a whole lot easier for new chemists to really visualize. When we talk about bond polarity, what we're really asking is, are the electrons shared evenly between atoms? We know in a covalent bond, you've got a pair of electrons, potentially more if it's a double or triple bond, being shared between two atoms. And in order to determine if they're sharing evenly, you want to look at differences in electronegativity. Now, we talked about electronegativity in the previous unit with the periodic table, and electronegativity is just the ability of an atom to attract electrons to itself in a bond. Remember, you can look up these values in Table S of the reference table. In order for a bond to be considered as nonpolar, the difference in electronegativity has to be very low. Somewhere between 0 and 0.4 is generally the range that we're looking at. Nonpolar means that electrons are being shared evenly or equally. If you think about the diatomic molecule H2, hydrogen has an electronegativity of 2.2. 2.2 minus itself is equal to 0. Diatomics are examples of perfectly nonpolar bonds. And if you were to visualize that, you've got two hydrogen atoms kind of like playing tug of war, if you will, with the electrons. And since they have exactly equal electronegativities, no one's winning or losing this tug of war battle. The electrons are shared evenly between the two atoms. Compare that to a polar bond. And in a polar bond, we see uneven sharing of electrons. And this comes from pretty big differences in electronegativities. I wouldn't worry too much about this range. I'd keep the number 0.4 in mind. 0.4 and lower, nonpolar. Covalent bond above 0.4, you see a polar bond. If we look at the hydrogen-chlorine bond, chlorine has a greater electronegativity than hydrogen. Chlorine is 3.2, hydrogen is 2.2, for a difference in electronegativity of 1. So we are not going to see even sharing. Chlorine is going to kind of hog the electrons. Got this wonderful picture to show that. Technically, the electrons are shared between the chlorine and the hydrogen atoms, but chlorine, since it's got a greater electronegativity, pulls the electrons towards itself. It's kind of hogging them in that bond. Just another way to kind of look at the bonds and the distribution of, how those electrons are shared. Nonpolar, we see that everything's kind of the same color, suggesting that there's very equal sharing between the two hydrogen atoms. If we look at the hydrogen-chlorine bond, we see kind of like a distorted cloud. Instead of them being shared equally between the two, we've got a higher electron density around the chlorine atom and a lower electron density around the hydrogen atom. This leads to partial charges. So from the reading, you might have come across this lowercase delta symbol. Looks like a little music note. Because the electrons are being pulled away from hydrogen, that's going to leave hydrogen to be a little bit positive. You can kind of think of that delta symbol as meaning just that, a little bit or slightly positive. Since chlorine is hogging the electrons and pulling the electrons towards itself, and we know electrons are negatively charged, the Cl in this bond, the chlorine atom, is going to have a slightly negative charge or a partial negative charge. Hopefully that makes sense. We're going to be applying this idea really of partial positive and negative charges to when we look at molecule polarity. Let's look at some practice problems. So before we get into looking at molecule polarity, let's just practice a bit with bond polarity. So you're definitely going to need your reference table unless for some strange reason you've memorized the electronegativity of all the atoms. So we've got a list of covalent bonds. We can quickly just eyeball them and know they're covalent because all of them are between two nonmetals. So to find the difference in electronegativity, I'm just going to subtract the lower electronegativity value from the higher one. So with carbon-hydrogen bond, I've got 2.6, whoops, sorry about that, 2.6 for carbon minus 2.2 for hydrogen. This is about as complicated as the math is going to get this unit. Hopefully no calculators required. I end up with a difference of electronegativity of 0.4. 0.4 and lower are nonpolar. Go ahead, pause the video and see if you can tackle the next, 5 different bonds. And we'll check in a moment. So I've gone ahead and written down the differences in electronegativity. Figure we'll just talk polar and nonpolar together. The OH bond is extremely polar. Oxygen is hogging those electrons. Fluorine and oxygen, that is also a polar bond. Fluorine will not bond to any other nonmetal in any other way than a polar bond. It's just way too electronegative. Nitrogen and sulfur, that will be a nonpolar bond. Remember, 0.4 and lower, nonpolar. Phosphorus and hydrogen, difference in electronegativity of 0, so that's definitely nonpolar. And last but not least, chlorine-oxygen bond, again, another really small difference in electronegativity, so that is a nonpolar bond as well. So when you're trying to figure out if a bond is polar or nonpolar, it's all about just looking at differences in electronegativity. Subtract them, 0.4 and lower, nonpolar. Above 0.4 and still covalently bonded, polar. Let's get back to the notes. Let's talk about molecule polarity. Molecule polarity tends to be conceptually a little bit more difficult than bond polarity, which is pretty cut and dry, just that simple subtraction. When we're talking about molecule polarity, what we're asking is, are the electrons distributed evenly throughout a molecule? If some of the bonds are polar and some of the bonds are nonpolar, one side of the molecule might start to pull electron density towards itself, causing an unequal or uneven distribution of charge. A nonpolar molecule has a pretty even distribution of electrons. If we look at something like methane, CH4, and I'm going to go ahead and just draw a quick Lewis structure. There we go. We know that the bond between carbon and hydrogen is nonpolar, and we also see that this is a really symmetrical molecule. Well, let's change my ink color and do a little bit more drawing. I could kind of fold this molecule in half that way, this way, and across the diagonals. Nonpolar molecules tend to be highly symmetrical. And in this case, all of the bonds are nonpolar, so it's really difficult to have an unequal distribution of electrons with nonpolar bonds. So this kind of green blobby thing is supposed to just represent the electron density or the distribution of electrons across a molecule of methane, the same throughout. Polar molecules, as you would probably deduce, have an uneven distribution of electrons. One side of the molecule is pulling electrons towards itself. The other side is electron poor. And a classic example of a polar molecule is water, H2O. Draw a quick Lewis structure. With water, we have a very electronegative atom, and oxygen, pulling electron density away from the hydrogen atoms. Polar molecules tend to be fairly asymmetrical. Maybe they'll have just one line of symmetry or 0 lines of symmetry. And those are two very general basic rules that will apply to most of the molecules we look at, but we will talk about how to determine molecule polarity in a little bit more detail. Again, just to focus on polar molecules, the atom with the greater electronegativity is going to pull the electrons towards itself. So just like we saw in our polar bonds, where the more electronegative atom is pulling electron density towards itself, the same thing happens in a molecule. So both the electrons in each of those bonds with hydrogen are being pulled towards oxygen. So oxygen is kind of hogging the electrons. As a result, we have a slightly negative, that little delta, almost looks like a music note, negative sign over the oxygen, telling us that that side of the molecule is slightly negatively charged. That's going to leave the hydrogen side of the molecule electron poor. So since electron density are being pulled away from the hydrogens, the hydrogen side ends up with slightly positive charges. Basically, this just means that polar molecules, such as water, will attract one another. They'll behave like little magnets, where the oxygen side of one water molecule will be attracted to like the hydrogen side of another water molecule. And when we start talking about solids, liquids, and gases, we will look more at the consequences of those attractions. So I want to just walk you through a flowchart on how to determine molecule polarity. It's a little bit more involved than just is this symmetrical or not. So really at the heart of determining polarity is drawing the correct Lewis structure. Got to make sure that you're remembering those unshared electron pairs, in particular, especially on the central atom. So the first thing we'll look at is, does the central atom have unshared electron pairs? If it does, there is an extremely high likelihood that the molecule is polar. Is this true 100% of the time? No, I'm sure you can dig and you can find some example of that not being true, but that's more of an exception than a rule. More often than not, unshared electron pairs on the central atom leads to a polar molecule. If you don't have any unshared electron pairs on the central atom, you got a little bit more work to do. You've got to look at the atoms that are bonded to the central atom and see if all of them are the same. That's the same question, just move the box so we can fit more on the screen. Are all of the atoms bonded to the central atom the same? If they are, you're looking at a nonpolar molecule. If not, you need to check to see if there are any polar bonds present. You might be thinking, well, wait a second, how come if they're all the same, like what if there's a polar bond there, wouldn't that make a molecule polar? Well, let's look at it. Let's take carbon tetrachloride, CCl4, as an example. No unshared electrons on the central atom. You've got chlorine bonded everywhere. Chlorine has an electronegativity of 3.2, carbon 2.6. So all of our differences in electronegativity are 0.6. That would make those bonds polar. But the electrons are being pulled towards the chlorines equally. So kind of the center of the negative charge is going to be, these will cancel each other out and end up in the middle, the carbon, and the center of the positive charge is also the carbon. So even with polar bonds, you end up with a nonpolar molecule. So if all of the atoms bonded to the central atom are not the same, check for bond polarity. If there are polar bonds present, you're looking at a polar molecule. If all of the bonds are nonpolar, then you've got a nonpolar molecule. Again, can you find exceptions, molecules that don't really obey this flowchart that we've put together? Yes, I'm sure you can. But the overwhelming majority of the molecules, and definitely the ones we look at this level, will obey this flowchart. Let's try to apply this to some practice problems. I'm back over in the practice problems with lesson 4.3, and I want to just work on completely filling out this table. So we've gone ahead and drawn Lewis structures, we've predicted geometries. The last two rows in the table are for predicting bond and molecule polarity. So hopefully bond polarity, again, pretty easy. We've got, in this case, silicon bonded with hydrogen, very small difference in electronegativity, 0.3. That's going to lead us to a nonpolar bond. What about this molecule as a whole? Is it polar or nonpolar? I don't have any unshared pairs of electrons on the central atom. I've got the same atom bonded to the central atom. This is a nonpolar molecule. Let's take a look at H2S. 2.2 for hydrogen, 2.6 electronegativity for sulfur, difference of 0.4, that makes it nonpolar. The bond itself, the molecule itself, polar or nonpolar? I've got unshared pairs of electrons on the central atom. Yeah, that's going to make the molecule polar, even if it's just slightly polar. NH3, ammonia. Nitrogen is 0.3, hydrogen 2.2. So a large difference in electronegativity, 0.8. So we have polar bonds between the nitrogen and hydrogen atoms. The molecule, let's see, unshared pair of electrons. This is a polar molecule. We've already talked about water, polar bonds for a polar molecule. Let's wrap up with those four. Pause the video, try it out. Tell me the bond and molecule polarity for these four small molecules. All right, I've gone through and I've identified the polarity of the bonds. Let's look at the polarity of the molecule. PCl5, phosphorus pentachloride, no unshared pairs of electrons on the central atom. That's going to make it a nonpolar molecule. Sulfur hexafluoride, SF6, again, no unpaired electrons on the central atom. That is also a nonpolar molecule. BBr3, boron tribromide, polar bonds, but no unshared pairs of electrons on the central atom. That's going to be a nonpolar molecule. And just to wrap it up, we have phosphorus trihydride, nonpolar bonds, but we do have an unshared pair of electrons on the central atom. Good chance this molecule is polar. All right, as always, keep practicing with the material. You've got plenty of practice problems to keep you busy. All right, thanks for tuning in, and I hope you found this helpful.